Alright, welcome back to the channel. In this video, I'm going to work with a quite interesting project that I really find online to extend some of the capability of Wolfram Language with external data source on regular graphs. And I'm going to show the code and how to generate this animation by yourself. So let's start from some simple ideas about regular graphs. So there are lots of different regular graph. Okay, so this type of graph is called a cubic graph, or it's called a three regular graph. So if you count a number of vertices, say in the first case it's 1, 2, 3, 4, 4 points, and the degree, which also means the number of edges attached to each vertices, is 3. So here it's 1, 2, 3, 1, 2, 3, 1, 2, 3. So it is for all points, the number of edges connect to that point is exactly 3. The same thing applies here. This is a 1, 2, 3, 1, 2, 3. So in total 6 points, and you have two types of graphs. And with 8, you have these type of graphs. And one of them, typically the first one, is not connected, and for the other 1, 2, 3, 4, 5 graphs are connected. This is a very well-known, very difficult problem to solve, and just given any number of vertices. Okay, first, it's really easy to answer the question with odd number of vertices. It is 0. You cannot have a cubic graph with odd number of vertices. So it only exists for even numbers, and the reference is inside the paragraph. But even with like very simple, I would say kindergarten level of setup math, it is extremely hard to find the exact number of graphs, which is you count it up to isomorphism. Say if you have numbers labeled on the graph, and if two graphs can be restored, or you can check the equivalence if you repermute the points on the graphs or the labels, and they coincide with each other. So for these graphs, they are pairwise non-isomorphic. So the question is, how many such graphs are there with say given odd even number of vertices, they are not isomorphic, and with a cubic graph property. This is quite difficult. There were some smart guy using large number of computing powers and curated the result online. So here is the website. It's called Math2Uni Berth. It's made Deutsch. It's a German guy, and he curated some of the numbers online. So the one I'm going to use is about a cubic graph. So it's degree 3, and with 18 vertices. And in this case, this also gives a number that specifies the girth, which is the size of the smallest cycle, must be larger than 3. So the graph or the data it's called is 1833. So you can download the data and play with the data. Okay, so this part of the graph was not built in the Wolfram Language graph data package. So we can use this external data to extend this capability of this product and generate the interesting animation we see at the beginning. Once you download data and put in the same directory of this notebook, you can just run this line so that this file it's sort of recognized in the system path, so you don't have to give the full path to read the file. Okay, so once you download the SCD file, you search online. There's probably no way for you to open this file because it's a binary file. It is quite large if we store the data of the graphs directly into the graph data form, or even the graph6 data format. So the author used a very smart compress the data format to store this demo. And you can import this directly inside the Wolfram language using the binary read data list, and using numerical array to make it as small as possible. And just use strong type of data. So let's just run the code. Okay. Run the code. Okay. Now this data is imported into Wolfram language, and you can click this plus sign to review part of the data. Okay. Also, you can just check the data in list form if you just wrap normal around this object. Okay, it shows you a list of data. Okay, and it is absolutely nonsense. If you don't know what's the meaning of this data, you probably won't be able to reconstruct the graphs that generated using these numbers. So let's take a look at how we reconstruct the graphs we see using a list of the number here. So the idea in the graph, in the original blog post, can be illustrated in 2 steps. And one is how to represent a graph in short code. Code for graph. And the second one is increment code for graph storation. Okay, let's first take a look at the graphs, the first part. We can go back to this web page, and let's see, it shows you how to use this one. Okay, here we go. Okay, so the first part is, let's say we have a graph, and how we efficiently save the information of the graph. So for example, if we have a graph with 4 vertices, the way to store it is the first graph, or the first point, connects to 2, 3, 4. And what I do is only store the number that's larger than the first one. So you have 2, 3, 4 in the list. And the second vertex, it connects to 1, 3, 4. And in this case, I only store the number that's larger than 2. And for example, if I have 3, it connects to 1, 2, 4, because it's a regular graph. So every point must connect exact 3. And the last, the number 3 must connect to 4. And 4 is connect to 1, 2, 3, but there is no number is larger than 4. So what we store is, for the graph, instead of storing 16 numbers, we only store 2, 3, 4, 3, 4, 4, 3. 4. Okay, 3 is omitted, of course, because there's no number is larger than 4. It's 2, 3, 4, 3, 4, 4. Okay. So this is the sort of the short code for our graph. And the next step is, if we do such thing for each graph, as we have more and more graph, it will be very inefficient to store that. So what it does is the second step is called increment notation, or an increment code. So what it does is, for example, we have number, ask AI to help you understand this kind of a compression. So I ask the Claude, and it actually gives me a very nice explanation of the compression technique here. Shows you exactly how this thing is applied. And because it is a rolling difference, which means once you have the first original graph and you compute the second one, and you have the second graph, and you compute the third graph, and it compares to the second one. So this will basically, the only thing that you change is attaching this notation again, and you do not have to write down the duplicated part for each pair of adjacent graphs. So in this way, this gives you a very nice compression of the data. You can also just go to this website and throw this URL into Claude or any AI. It would just explain things to you. And I think this graph really helps me to understand how this guy is used to sufficiently store the data. And through this, I just don't have to use the API or the C code they have given to me. I just re-implement it in the Wolfram language, and it works like charm. So for this to work, you do have to remember that it only works with regular graphs, because in regular graph, the number of edges and the number of points, vertices, are fixed. For any just general graph, this method won't work. Okay, so using this AI, the explanation from both the website and the example given from AI, I actually implement this code by myself to easily convert this guy into a list of graphs. So let's check how it's done. So first, this is a number of data points. It's same thing as 250392 here. So I just use it here for some easy access of the length of numbers. And it's really easy to show that in my code. Originally, this I just hard coded to put the 27 here. Okay, but you can actually compute 27 from 18 times 3 over 2. The reason why it works is, for example, if you have a graph, okay, of course you have 18 vertices, but each vertices have 3. So the number of edges is simply the half of number of all the edges, all the degree of the vertices add up and divided by 2. So it's 3 times 18 divided by 2. And this is a generic formula, works for all the graphs. So it's just a variation of the number of edges equal the sum of the degree of the vertices and divided by 2. So this is a very generic formula, but it's particularly nice for regular graph, because I know the number of vertices is 18, and I know each degree must be 3. So 3 times 18 divided by 2, you have 27 here. Okay. And the first step is just check the number of edges. And the second step is just the use definition I have to find the flags point. What's the flag position is just, let's go back to the diagram given by the Claude. So what I do here is first read all the graphs of the vertices through the first part. In this case, there will be exactly 27 numbers plus the leading 0, because this indicates this is the first graph that as or called the first or base graph or original graph that I start with. And the flag position is exactly the position of these numbers. So it will indicate how many numbers or how many the length of the prefix that shares the same length. And for these part, I will just skip or easily compute the length of the diffs, because in the example, for each graph, they will have exactly 27 edges, and minus the number of the prefix will give the number of the elements that shows the difference between two graphs. So this is exactly this part. So if every time you have the position of, you show the position of this guy, and the next 6 is exactly a skip of the length of the different parts. So this is exactly the idea of this guy. But of course, because you are looking for the position of the next flag, so you have to add a 1 at the end. So this is the current flag plus the number of edges minus the length of difference and plus 1. And in this case, you will find all the positions in the list above. That gives you the number of the length of prefix in each adjacent graph. And in this way, you can just check that the flag of the length is exactly 41301, because there are exactly 41301 non-isomorphic graphs in the list. And then we can convert that to each list given the flag position back into graph. For example, if I start from this base graph, so this is the number of the name of the vertices that's used for construct the base graph. Let's see how we can reconstruct the base graph through these guys. So we will just do partially of the reconstruction. So for example, it start with 2, 3, 4, 3, 4, 5, 5, 6, 7. 2, 3, 4, 3, 4, 5, 5, 6, 7, 8, 8, 9. Okay. This is the shortcode for our graph. Which means the first element is 1. It connects to 2, 3, 4. Okay, we use that. And the second one, it connects to 1, because it's connect to 1 in the first case. It's connect 1, 3, 3, 4, and 3, 4 used. And then the third one connect to 1, and also it connects to 2, and we have to use 5 here. Okay, 5 is skipped. And then 4 connect to 1, 4 connect to 2, and 4 connect to 5. 5 is used. Okay, and what about a 5? 5 connect to 3, it connects to 4, it connects to 6, and 6 is used. Okay, so it's same thing like this, and it keeps going on. And I'm also have a code that does the conversion from the shortcode back into the connection graph using data structures. And I'm going to show that in the slightly later after our example here. So this is exactly the base graph. We have to drop the first item. Remember, the first item in the code is always 0. And we have 27 items. That's why it's from 2 to 28. So this is the base graph. And we can also randomly check a flag. And this is exactly the position of the flag. And this is an actual index of the flag in the original compressed data. And the 25 is exactly the value associated with that index. The graph associated with this number, there are 25 numbers that share the same bits as the previous graph. And I will check the next 2 items in this compressed form to reconstruct my graph. And because it is a rolling graph, it's a rolling difference, you do have to use the nest function to compute all the graph from 1 to the graph that really before this guy, and just check them one by one and till and use the number. It's not all the graphs comparing the first one, but it's a rolling difference. So we can use 2 functions. It's kind of similar. One is just to use nest, and the other use nest list. So in this case, basically it gives you everything, and then you just store all the data in a very long list. And it's easy for me to work on that later, and we don't have to redo the nest again. And for this guy, it just compute exactly 1. So if you just do want it once and want to save memory, this is the function to go. And if this is something that you want to just store everything by yourself, you don't have to worry about doing the nest again. Just simply run everything, and I will do it. Just store the result for you. Okay. So I can choose to run that for first, and run that for the next part. And for the sake of saving memory, I can just use numeric array to wrap everything inside a very compressed form. So you can check this guy. It is really large because this is the number of graphs, and this is the length of bits. Okay, so now in this case, everything is like this shortcode. So it does have a lot of duplications, and it's kind of very inefficient way to store that, comparing to the original data we have here. So it would be definitely more space to use, but still using this typed storage, it's still much better than just to store it in list form. So in this case, you can just work with parts exactly like a list you have. So if I want to get the second non-isometric graph, is simply using 2. And if you want to see the list, it's simply you just wrap normal around it. And you can just extract the 100th to that, okay? So this gives you the graph associated with each shortcode. Okay, now let's do a conversion. The conversion uses a couple of data structures to, maybe it's not the best, but I think this is the most straightforward way to create this construction. So the idea is really simple, just like the manual ways I have done on the whiteboard. So what we do is, if we have a shortcode, let's just using the shortcode here. Let's see, using the shortcode. For example, the 100th. Okay, it's 2, 3, 4, 3, 4, 5, 5, 6, 7, 8. Okay. So how do you convert that is first you have a loop. It's from 1 to 17. Because definitely you don't really need 18 for that work, because 18 is the largest one. Even though it connects to some vertices, but there is no number is larger than 18, so I don't have to store anything about 18. And at meantime, I also have a list. So it contains 17 numbers. 17 numbers. At the beginning, everything is 3. So there's 3 times 17. There are 17 copies of 3. Okay, it's very, very straightforward. And Wolfram is 1 based. So 1, 2, 3, to 17. Okay, it's very, very straightforward. The next step is you simply loop it. What you do is say, the first number is connect to 2, 3, 4. And I have used 2, 3, 4 once and 1 once. So what I do is simply I use 1 3 times. So every time you have 2, you just minus 1 in the list. Say in this case you have 2, 3, 4. So for 1, because it connects all 3, so the first one is simply 0. And now 2 is 3 minus 1 because you used only once. And the 3 used once, and the 4 used only once, 2, 3, right? And this is very mechanical. So every time you use it, for example, then I start with 2. 2 must connect to, according to the list. So I already used that. It's 3, 4. And also it connects to 1, right? So it connects to 2 and 3. They are larger than that. So I use 2 twice. So in this case, 2, the list becomes 0. 2 used twice is 0. And I use 3 once here, so it becomes 1. And 4 becomes 1 here. 3. And you can see, so every time I check, loop through the elements, I would just skip some of the numbers that with 0 ahead of it. And for any number that's larger than, if it does not show up, or I just use that new number minus 1. And 2 is all, for example, the next one, the 3 will be minus 1. So every time I just choose the number that's not 0 in the list, and I want to go through the loop. So this is exactly the code that shows here. So if the number is the CT array is the number that I was talking about with initially 18 or 17 copy of 3. That's really doesn't matter because for the last one I just choose run like 17 times. So the last one can never be changed, or you can just skip it. And the idea is if the number, the count of that number is greater than 0, and the stack is not empty. Stack is simply the original list of numbers. I store them in a stack. So every time I use one number, I just do a pop. So that number will get out. And also I want to keep the sequence. So here is the way that you actually how you keep the sequence in that one. So stack is say you have to put 2 at the last, because stack is first in, last out. So this is the correct order to use a stack in this case. And this guy is simply count how many times a number is used, because every number or each vertex, the degree is exactly 3. So more than 3, you basically don't have you don't have to check that number anymore. And also you want to make sure that if the number is less than the top, so if it's less than the top, it's definitely the top will be the next or the edge, the next vertex attached to the same edge of the that's starting with the number k. So with these three, so you start to build your edge, and the edge is simply the dynamic array that every time you have the number that larger than the number of k, you just put them into a dynamic array. So you just append it into a dynamic array. So this gives you a pair of tuples, or it's simply the edge. So let's just run the code to have a quick look at the ideas. And every time we run that, we have to just reset everything and check the whether these edges are valid. So every time I run it, I can just using this code to enumerate all the non-isomorphic graph that I need in this case. Okay, this is very clear, and it runs really smoothly. So this gives you the idea about how to do the conversions for the short code back into our graphs. Okay, it's very clear. Alright, this video seems a bit too long than I expected, so I'm going to cover the animation generation part in a short video in a separate part. Alright, let's conclude this part and have a good time. Bye bye.